Okay, we are going to continue on here. Chapter 12, been talking bonding, I think. Chemistry like, I think. So we talked about some different types of bonding. The two major sort of categories of bonding is ionic bonding, which as we talked about is always between a metal and a non-metal. And remember that it really is a lot of those periodic trends that we talked about which allow metals to essentially want to give away their electrons. And non-metals pretty much have all the opposite sort of periodic trends where they want to kind of gain the electrons. So whenever we get these two guys together, we're always going to result in a transfer of electrons there from our metal to our non-metal. And the result of that, as we talked about, is we will make some ions, and our metal will make our cation, which is positively charged. Our anion will come from our non-metal, which is negatively charged. And one of the main things that we talked about in terms of this type of bonding is, again, there is no sharing of electrons happening here. So it really is that electrostatic attraction between the positive and negative ions that hold that together. So no sharing of electrons. And that's different than really the other sort of major type of bonding we talked about, which is covalent bonding. And in covalent bonding, that is usually between two nonmetals. And because nonmetals pretty much reside in the same spot on the periodic table, they both basically have the periodic trends where they really both want to hang on to their electrons. They really both want to actually take electrons. So really the best that they could do is maybe agree upon, since nobody's going to weigh their electrons, is to share electrons. So in this type of bonding, we do have sharing of electrons. And as we talked about, that sharing can be equal sharing of electrons, which creates a nonpolar covalent bond. We could also have a case where the electrons are not shared equally. And that results in a polar bond. Remember that it is, as we were talking about towards the end there, electronegativity that really is sort of the big overwhelming sort of factor as to whether or not those electrons will be shared equally or unequally. And there is sort of a consequence of the sharing of electrons. For example, if we had something like our F2, that's going to create a nonpolar bond where the electrons would be shared equally. And as we talked about, essentially that bond's going to be pretty much like a neutral bond. There's not going to be a side that's going to be more positive or more negative, real sort of separation of charge. And that's different than when we swap out one of those fluorines in that case for a hydrogen. Now there is a big difference in electronegativity, with fluorine being the more electronegative, that we could draw that dipole arrow heading towards the one that is more negative in the bond. And this backside again to the more positive. And that creates, as we talked about, the sort of partially negative charge and partially positive charges on these two elements within this bond. And it does create this sort of charge separation that occurs from the unequal sharing of electrons. As we'll talk about again in some other chapters along the way, it plays a really big part in some of the properties of certain molecules, depending on whether they have polar bonds or do not have polar bonds. We also talked about that it is, again, partially positive and partially negative because there is still some aspect of sharing that's going on there. So no electrons have been fully transferred, like we see in ionic bonding, where we get a full positive, full negative charge, but we do get this sort of separation of charge. We talked about electronegativity, and just a reminder again that as we go up and to the right on the periodic table, it increases with fluorine being the most electronegative. And decreases as you go down. We also talked about in the aspect of ionic bonding, drawing Lewis dot symbols to help us understand what is going on with that. Remember that a Lewis dot symbol or an electron dot symbol is really just a symbol with one dot to represent the number of valence electrons that it has. And remember that the number of valence electrons equals the group number. So the group number will tell you the number of valence electrons there are. And again, if we had something like fluorine, which is group 7, once again, in this case, we're going to get that transfer, making Li plus and F minus. Remember that both ionic bonding, covalent bonding, it really doesn't matter. The whole point of bonding is for everybody to achieve the same electron configuration as the noble gases because they're very, very stable. Remember that they don't turn into those noble gases because we're not doing anything with the protons, but their electron arrangement basically becomes the same as those noble gases. And that's why, again, really the whole point of ionic bonding, they achieve that by the metal losing electrons and backing up on the periodic table to the noble gas that comes before it. Nonmetals gain the electrons, they go forward on the periodic table to the noble gas that comes after them. And in the case of covalent bonding, they essentially achieve that through sharing of electrons. So again, through that sharing of electrons, they're able to achieve that magical number of 8, right? Which, as we talked about, is the octet rule, which is obviously really important for bonding. And also, as we talked about, hydrogen should only have 2 electrons, right? Because it just needs to get to helium and should never have more than that. Any questions on any of that stuff there? All right. So I think we laid out sort of an electronegativity, I think. So let's continue on there and talk about that. A guy by the name of Pauling devised a method for calculating electronegativity values for the elements. He basically had a scale that ran from 0 to 4, 4 being the most electronegative. 0, not so much. Yeah. So not very electronegative pretty much at all, no electronegativity. That, by the way, is typically what you would use for noble gases because they're not looking to do anything. They're really stable the way they are. They're not looking to gain electrons or lose electrons, so they have sort of a 0 in terms of electronegativity. So a lot of times we could use electronegativity values if you're not sure to help you decide what type of bond you would be dealing with, how those electrons would be shared. We typically calculate, sometimes referred to as the change in electronegativity values. So that delta means a change in electronegativity values. And frankly, you just subtract the 2 electronegativity values for each element. You do it in a way that gives you a positive number. So whichever one's larger, just subtract it from the smaller one there. And if you do the difference in electronegativity values and get anywhere from 0 to about 0.4, that is considered a nonpolar covalent bond, where we would count it as basically sharing those electrons equally. Now, clearly, that's a big range there, 0 to 0.4. So 0 would be kind of perfect sharing of electrons. 0.4 is still not perfect sharing, but is close enough to still be considered nonpolar and equal sharing. So anything above 0.4 to below 2 is considered a polar bond, and unequal sharing basically occurring in that case. And in general, anything above 2 is typically considered an ionic bond, where there's absolutely no sharing but transfer of electrons. I will say that that 2 is sort of an arbitrary number, and there are examples where you will have an ionic bond that has a difference that's less than 2. So the good news is, frankly, you really don't even need the electronegativity values for ionic. As soon as you see it's a metal and a non-metal, that's good enough, right? Ionic, go on with your life. It'll be okay. In that case, you don't have to really use electronegativity values to figure it out. So I would suggest that the electronegativity values probably you would want to use more so for covalent bonding. And again, just remember metal, non-metal, ionic, I wouldn't even worry about it. Now, there is, like I said, sort of a range of equal sharing. And sometimes when you get a difference in electronegativity value of exactly 0, sometimes books will classify that as a pure covalent bond, which is essentially still a nonpolar bond, but they sometimes will distinguish that as like the perfect equal sharing of electrons. Again, it's still equal sharing of electrons, just like 0.4 would technically be nonpolar and equal sharing of electrons. But in reality, 0.4 difference, there is a little bit of unequalness happening there, but not to the degree that is considered unequal enough to be polar in that case. Any questions on that there? So if we look at a table such as this, different electronegativity values, and you can see for different elements, there's some different values. And clearly these values would be provided for you if you needed them. That's crazy to make you remember this. You should know, though, the general trend in electronegativity, again, that it increases as you go up to the right and decreases as you go down. So if we just look at some of the ones that we looked at previously, like NaCl, little HF, and like F2. So if we were to use this, we would basically just look up the values for each of these elements. So if we look up sodium there, it is 0.9. Chlorine is 3. So the difference in electronegativity is just 3 minus 0.9 gives you 2.1. That is above 2, and it would be ionic in that case. But once again, you really don't need it because that's a metal and a non-metal, so it should be ionic. And the reason why I tell you that the 2 is sort of arbitrary for that is you could come with some combinations where you would get less than a 2 difference. For example, if you did like lithium and bromine, the difference between that would be 1.8, but it's still an ionic bond and it's obviously less than 2. So 2 is just a rough cutoff for ionic. And again, as I mentioned, just the metal, non-metal is really what you should think about in terms of that. If we look at F and F here, it both have an electronegativity value of 4, which means our difference in electronegativity here is going to give us a 0, and that falls under the 0 to 0.4, which would be a nonpolar bond. That would definitely be covalent, as it's 2 nonmetals together. And that would also be classified sometimes as a pure covalent bond, as the electronegativity value there is different. If we look at HF, H is 2.1, F is 4. So our difference in electronegativity is 4 minus 2.1. That's like a 1.9, I think. 1.9 is at the top end there of the polar scale. And we draw that arrow again pointing towards the fluorine. That is more electronegative. So you can use these values if you're not sure. Polar, non-polar covalent bond. Again, just simply take the difference in those values and larger minus smaller. This is what is sometimes referred to when you take the electronegativity values to determine whether or not the bond is polar or not as bond polarity. So when we use these electronegativities, this is what is referred to as bond polarity. And basically what that is telling you is, for the most part, just between those two elements, how those electrons are shared. Now, if there happens to be other bonds involved, there's some other things that you have to take into account. So that is what we kind of use bond polarity for. The only place where bond polarity and molecular polarity are the same is something like what we got up there on the right. Because there's only one bond in each of those cases, that one bond is nonpolar, for example, so the molecule would be nonpolar as well. And for the HF, it only has one bond, so that bond is polar, then it would be a polar molecule as well. So for diatomic molecules, that is the only place where you can use like bond polarity, the difference in electronegativity, and it will also tell you if that molecule itself is going to be a polar molecule or non-polar molecule, again, because it only contains one bond. We'll talk about at the end of the chapter, when you have 3 or more atoms involved, there's a couple other things you have to kind of take into account to determine molecular polarity. So there's 2 types of polarity we'll talk about. This is, for the most part, bond polarity here. So why don't you try some here? Why don't we do the bond between potassium and bromine? We'll do carbon and oxygen. We'll do carbon and hydrogen. We'll do sulfur and oxygen. We'll do a little carbon and sulfur. So for each of these, use the electronegativity values here to determine is it polar, ionic, or nonpolar. And for anyone that is polar, draw the arrow heading C. So we'll start with the KBr. So if we were going to use our electronegativity values, we got a 0.8 for the K, and the BR there is 2.8. So our difference in electronegativity would be 2.8 minus 0.8, which gives us a 2, and that would be an ionic bond. Once again, we don't actually need any of those values because we have a metal and a non-metal, so we should just know that it is going to be ionic in that case. Any questions on that one there? Looking at our carbon and oxygen, our carbon has a value of 2.5. Our oxygen there has a value of 3.5. So if we do a difference in electronegativity, that's going to be 3.5 minus 2.5, which is 1. That 1 is above 0.4, right? But below 2, so that falls in our polar range, with the oxygen being more electronegative. So we would draw the arrow heading towards the oxygen. Again, that arrow is sometimes referred to as the bond dipole arrow. Yeah. Any questions on that one? Coming over here to carbon and hydrogen, carbon going to be 2.5, hydrogen going to be 2.1. So our difference in electronegativity, 2.5 minus 2.1, 0.4. 0.4 means that this is going to be nonpolar. That's like the upper limit of nonpolar. And really the reason for that is pretty much organic chemistry. Most organic molecules are carbons and hydrogens together, and carbons attached to carbons, and they're nonpolar. So that's why that sort of upper limit goes to 0.4 to cover that carbon-hydrogen bond, and it would be nonpolar. As I mentioned before, doesn't mean there really is perfect equal sharing of electrons in this case. It is hedging a little bit towards the carbon in this case, right? But again, not enough to be considered polar or unequal sharing in that particular case. If we look at, we got there sulfur and oxygen. Sulfur there is 2.5. Oxygen is 3.5. So again, our difference in electronegativity going to be 3.5 minus 2.5, going to give us a 1. That again is going to tell us that this is going to be polar. And if we were to draw that arrow, again, it should head towards the more electronegative atom, which is the oxygen in this case. Lastly, looking at carbon and sulfur, carbon 2.5, sulfur 2.5. Difference in electronegativity is going to get us a big 0 there. That means that this is actually a nonpolar bond. So this is a good example that it is possible to have two different elements that do share the same electronegativity and will lead to a nonpolar bond. Any questions on how to calculate any of that? Yeah. It's a bond dipole arrow. Yeah. Other question? Yeah, it's only for polar bonds, and you always, again, point the arrow part, the pointy part, towards the negative side, the more electronegative. And the back end that kind of makes like a plus sign always goes to the more positive side of it. That's a good way to remember. It kind of makes like a plus on the back end of it. So that goes to the more least electronegative side. Other questions? All right, so why is that? If we look actually on the periodic table, there is a reason why that is. If we look at the difference where sulfur and carbon is, they are what we like to call diagonal of each other on the periodic table. So carbon is further up, but sulfur is further to the right, so they negate basically their differences. It's not right underneath, kind of down and to the right. And there's a few places on the periodic table where you see that diagonal relationship. You also see it with nitrogen and oxygen as well, for example. And a few other places, you know, if you were to look as well, there's sort of some diagonal sort of relationships that occur. So you do want to be careful. Just, you know, if you're not sure, kind of look at it and just go, is it kind of down and to the right diagonal of each other? They might actually be pretty close in terms of electronegativity. Now, in certain cases, frankly, you don't necessarily need the actual values. You could use the general trend in electronegativity to determine whether or not something would be polar or nonpolar and make a pretty good educated guess. So for example, if we look at our carbon and oxygen, they're in the same row on the periodic table. and oxygen is further to the right, which means that oxygen should be more electronegative, and that should yield you a polar bond. So if you're comparing somebody on the periodic table that's in the same row, and one's further to the right than the other, probably a pretty good bet that it's going to produce a polar bond, and you really don't need the values to sort of figure that out. Also, if we looked at sulfur and oxygen, which was another one we did, they are in the same group on the periodic table, and oxygen is further up on the group, and that means it should also be more electronegative and should produce you a polar bond. So if you're comparing somebody in the same group or this on the periodic table, you could probably make a pretty safe guess as to it's going to be a polar bond just by their locations to one another within either the group or the period, and you don't really actually need the numbers. So a lot of times people always think I always need the numbers, always need the numbers. You don't necessarily always need the numbers. You could usually make a pretty good estimate just based on where things are located. Any questions on electronegativity values, how to use them? So once again, numbers would be provided, but you need to know the trend of up and to the right increase and down to the left decreases. So as we saw there in some of those examples, atoms with widely different electronegativities tend to form ionic bonds. So that's really what happens when we get somebody that's on the left-hand side of the periodic table, like our metal, and somebody on the right-hand side, upper right, that's our non-metal. We're going to get those transfer of electrons. And atoms with very similar ones will tend to form covalent bond, and that's why we have our nonmetals typically form those covalent bonds because they have similar electronegativity values. And again, that's what results in the different types of bonds that we've talked about. So as I mentioned before, although there's not a distinct, sharp distinction between polar and ionic, that 2-ish is sort of the cutoff, but as we saw there are some examples where it's not perfect. So again, that metal, non-metal is what you want to kind of think about. Not often outside of the book, people sometimes sort of identify bonds by percent ionic character rather than polar, non-polar, or ionic. I guess that's sort of ionic. So things that are ionic bonds is basically 100% ionic character. So an ionic bond is obviously 100%. A nonpolar bond or a pure covalent bond would be closer to the 0, and obviously our polar would be somewhere in the middle there between 0 and 100. Not too many people use that these days to sort of describe bonds. Most people go with the big three of ionic, polar, or nonpolar in terms of ways of describing bonds. But you sometimes will see that still used. So in this case over here, this would be more 100%. Over here would definitely be 0% as that's a pure covalent bond. And obviously our guy there in the middle would be some percentage in the middle of the two as well. All right, so earlier we talked about drawing Lewis sort of symbols and structures for ionic compounds. We're now going to talk about the steps that you should follow to draw Lewis structures for covalent compounds where we're sharing electrons. I would highly recommend that you follow these steps because it should lead you to a pretty good structure when it's all said and done. I would also highly recommend that you don't do sort of what people try to do, which is like piecework. Like they just draw the dot symbols for each element, try to figure out where all the electrons go and try to put it together that way. And usually what happens when people do that is they end up with too many electrons, not enough electrons, wrong number of bonds. But if you sort of follow these steps here, where we sort of think about the electrons as not necessarily belonging to a particular element, and just that we need to distribute these electrons sort of equally over the entire molecule will usually lead you to the right sort of structure. And that's where people kind of piecework wise get into trouble. They go, well, nitrogen came in with 5, so it needs 3. Oxygen's got 6, so it's going to need like 2. And they try to figure out where it all comes from, and they kind of screw it up. So let's talk about the steps here to draw these things. The first thing that you really want to do is think about how the compound is put together if you're not sure. What is sort of the skeletal arrangement? There are a few things that can help you decide where to put things. In the center position is least electronegative element. So you want to put the least electronegative element in the center. That also means that typically we do not see hydrogen or fluorine in the center because fluorine is the most electronegative, and hydrogen obviously can never be in the center, as we talked about, because if it's in the center, it's definitely going to have way more than 2 electrons, right? So never ever put that in the center as well. Also, logic helps a lot here. If you have one element and like 3 atoms of a different element, usually the one element's in the middle and everybody's attached to it is usually how it goes. It is possible to have multiple center atoms. Most of the time, though, probably in this class, most of what you'll draw probably will have just one guy in the middle and everybody attached to it, but it is possible to have multiple sort of central atoms and things attached. Probably the most important thing is number 2, and that is counting the total number of valence electrons in the entire molecule. Remember, again, the number of valence electrons equals the group number. And we want to add up to, again, just the grand total of how many valence electrons should be in your picture. And again, that number is really important because when you're done with the picture, you got to hit exactly that number. So you can't have any more, you can't have any less. You got to be dead on that number. Now, you could come across something that you need to draw, which are known as polyatomic ions. Polyatomic ions. So the charge here is kind of similar to what we talked about. If you have one that has a negative charge, negative means that it has gained electrons. So you need to add that charge to your total number of electrons. Otherwise, you will not have enough electrons in your picture. And if something has a positive, which I changed, it might have said negative on your chart, but it should be positive. That means that it has lost electrons. So you need to subtract that from your total. So that is really important. I will say again, in our class, everything will obey the octet rule, which means you never should have an odd number when you count up all your electrons. It can happen. It definitely could happen. But for the most part, what we'll draw will pretty much always have sort of even numbers. But again, it is possible to have an odd number, but very rarely in here that you would draw something maybe like that. Once you have sort of the arrangement of how it should be put together, and you have how many electrons that you need to do, the next thing that you want to do is draw one single covalent bond from the central atom to each of the outside atoms. I personally use lines to do that. Remember, each line represents 2 electrons, and just want to do one single bond to everybody. Once you do that, you have used a certain number of electrons, and you'll have a certain number of electrons left. So you're going to basically draw a single bond to each of those guys on the outside with a line. And then all the leftover electrons that you have will go on the outside atoms in pairs of dots until each of the outside atoms have 8 electrons, right, which is our octet rule. And then if you fill up all the outside atoms with electrons and you still have electrons that you need to put on your picture after you fill up everybody on the outside and you still have electrons, then you go to the central atom and put them on as dots as well. So that's sort of the process. Single bond, not double, not triple out of the gate, single bond. Fill up all the outside with dots, pairs of non-bonding electrons. Any leftover electrons go as pairs on the central atom. At that point, once you get to the central atom and start putting dots, you should definitely be out of electrons at some point. And you want to check, lastly, that everybody has met the octet rule. And again, that means that everybody has 8 electrons around it, except for hydrogen that should only have, again, the 2. And it's at that point, if somebody does not meet the octet rule, that is where you should lay up some double bond to try to fix it. And if the double bonds don't fix it and you've exhausted all your double bond opportunity, then you should move on to triple bond. So that is really the best order to do it. Again, people always want a double bond, triple bond right out of the gate. You should really save that to fix a situation where somebody does not meet the octet rule. Questions on that? All right, let's do one together so we can see all these steps happening here. So we want to draw the Lewis structure here for NF3. So the first thing I'm going to do is add up the total number of valence electrons. So nitrogen is group 5, so it's got 5. There are 3 fluorines. Each is group 7, which means they have 7 valence electrons. So that's 21 and 5 is 26 valence electrons is an important number. That number is dead on where we need to be when our picture is all said and done. At this point, between nitrogen and fluorine, nitrogen is the least electronegative element, which should go in the center. By the way, we should never put fluorine in the center, but we also have 1 nitrogen and 3 fluorines. The fluorine should go on the outside. I'm just going to kind of put them around. And to answer maybe a question somebody might have, it doesn't matter. I could put that fluorine on top or bottom. It doesn't matter where I put that kind of third fluorine there. Now that we have the arrangement, now that we have our electrons, the first thing that we want to do is just do one single bond from the center to the outside atoms. If we add up how many electrons we just used, that is 2, 4, 6. That is 20 electrons that I still have to put on my picture. So again, they're going to go on the outside in pairs of electrons, which are dots. So 2, 4, 6. That one is filled because it has 8. 8, 10, 12, 14, 16, and 18. So I just put on another 18 electrons. That means I still have 2 more to go in this case. Everybody on the outside is filled because they all have 8. Those last 2 electrons now move to the center, and they also go on as a pair of dots, which now I've used up. The last thing that I want to do is make sure everybody meets the octet rule, and everybody should meet the octet rule here. In this case, we got 2, 4, 6, 8. These are all the same. So 2, 4, 6, 8, 2, 4, 6, and 8. And if we look at the nitrogen in the middle, it has 2, 4, 6, and 8. Doesn't matter if they're lines or dots, right? That count as electrons. Everybody has met the octet rule, and that would be, without the highlighting, the correct Lewis structure that you should draw. Any questions on that there? All right, then why don't you try one here? Why don't you draw the Lewis structure for, not this one we just did. Why don't you do NO3 minus? So draw a Lewis structure here for this guy. 19, 24 valence electrons in this case. So again, it's important if it does have a charge that you do sort of adjust your total number of electrons so you have the correct amount. Once again here, nitrogen and oxygen, if you look at the periodic table, it looks something like this. Oxygen is further to the right there, which means it's more electronegative. So nitrogen should be in the middle. And once again, we only really have 1 nitrogen, 3 oxygen. So the one guy usually in the middle is what you want to look for. So we're going to do a nitrogen here in the middle, oxygen's around. We're going to do our same thing, a single bond to each. So that is now used 2, 4, and 6 electrons, 2 for each line. So I do a little quick subtraction there. 18 more to go, I think. So those 18 are going to go on the outside, again, as pairs of electrons, non-bonding electron dots. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons in this particular case. At this point, my picture has all 24 electrons on it. Is everybody good in this case? The oxygen's good. The oxygens are good, right? It's got 2, 4, 6, and 8. They're all the same. Nitrogen is not good. Nitrogen only's got 2, 4, and 6, right? So a little short in terms of our nitrogen. So we do need to fix it. So we got to make sure he has 8 electrons. So can I fix it by doing this? Can I just put electrons there? I cannot, because now I have a grand total of 26 electrons, right? Which is too many, so we cannot do that. So this is a situation where we need to fix it by trying to make a double bond. And in this case, each of the oxygens that we see are pretty much identical. They're all identical oxygens, which means you can make a double bond at any of the oxygens that you choose. So if I want to make a double bond here at the top oxygen, can I just draw the line? I cannot for the same reason. I now have 26 electrons, and the oxygen up on top now has like 10 electrons, which is way too many for that oxygen. So when we actually go to make a double bond, we are actually going to be taking a pair of electrons and we're going to be bringing them in to make that double bond. So we're just going to grab a pair of electrons and bring them in to make that double bond. The result of that is we will end up with a double bonded oxygen up on top. We will still have our single bonded oxygen on the right and left. And typically we do put a bracket around it since it is something with a charge and put the little charge on the outside. By doing so, that allows us to have still 24 electrons only. The oxygen up on top has 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8, 2, 4, 6, 8. And now our nitrogen there in the center will also have 2, 4, 6, and 8. So it allows everybody to again get to that 8 number and still maintains the proper number of electrons. Question on that there. Now, if you did lay up your double bond to the left, you would have a structure that looks something like this. And we had our original structure there, looks something like this. And you could have, again, also laid up a double bond there to the right, something like this. All three of these structures are perfectly okay to draw in this case. They're actually related to each other. That's what the little arrows mean. These are what are referred to as resonance structures. And resonance structures are pretty much what you just see there. We had more than one location where we could lay up that double bond, so we could draw another structure where we just kind of move the double bond to all the possible locations. The reason for that is those double bond electrons that we brought in to make the double bond are what are sometimes referred to as being delocalized, which means at some given point in time, they may be over here. At some other given point in time, they may be up there at that oxygen, or they may be over there at the oxygen and the right, which means probably the true structure is somewhere between all three of these. And that's why we can draw these sort of resonance structures, because they're sort of moving around those double bond electrons to each of the oxygens in this particular case. So if you were asked this question to draw a Lewis structure for nitrate, any one of the three would be sufficient. If you were asked to draw all the resonance structures, you have to draw all three of the structures that are there. Any questions on that? All right, then let us continue to draw. Why don't you draw these Lewis structures and we'll see how it goes here. So let's do that. Let's do that. Let's do this. Let's do this guy. Why don't you draw nitric acid too? Why not? And in case you're not sure how nitric acid looks, it looks something like this, is how it's arranged. And why don't you also do CO2? All right. So for each of those, draw proper Lewis structures. And we'll talk about it. I'll take a nap. You draw. Good. Okay, so let's see how you're doing on some of these here. We'll start at the top, which is hopefully where you started. We'll look at SH2. And again, I'm going to count up the total number of valence electrons that there are. So sulfur is 6. There's 2 hydrogens, each at 1, which means, again, my picture here should have 8 valence electrons. As we talked about a number of times up to this point, never going to put hydrogen in the middle. So that leaves sulfur to go in the middle. And we're just going to put our hydrogens on either side. Truthfully, you could go up and down if you want. It don't really matter, but most people just kind of draw it straight across. We're going to do our same thing. We're going to draw one single bond from the center to each of the outside atoms. And that's going to be 2 and 4 electrons that are left over. We have 4 more electrons. Am I going to put dots on the hydrogen? Correct. We don't want X's on our paper, so we're not going to put any dots. Again, a reminder, no dots, no double bond, triple bonding hydrogen, no double bonding, triple bond hydrogen and dots. None of those are good combinations. Pretty much that's what hydrogen should always look like in your picture when you draw it, just like that on the outside, one line going to it, and that's all it should be. So that means that our leftover 4 electrons should end up on the center atom. Once again, they are going to come on as pairs of electrons, which are represented as pairs of dots, obviously here. And that's going to give us our 2, 4, 6, 8 electrons for our sulfur in the middle. Also going to give us 2 electrons for each of the hydrogens. And again, that is all hydrogen needs. And that should be our correct picture in this case. Any questions on that one there? All right, so we're going to go over here to SO2. We're going to do the same thing. We got 6 for the sulfur. There are 2 oxygens, each has 6. 18 valence electrons is what we should end up with here. Now, in this particular case, sulfur should go in the middle with oxygens on the end, or sides. As if you look at the periodic table, oxygen and sulfur in the same group, oxygen being more electronegative. And also in this case, we have just 1 sulfur, so put it in the middle. We're going to do our same process here, a single bond from the center to the outside. That's going to use up 4 electrons. We have 14 more to go. So we're going to put those on the outside. So 2, 4, and 6. And now that is filled with 8 total. 8, 10, and 12 at this point. At this point, I have only put on my picture 16 electrons, but I still have 2 more to go. And that needs to go on the center atom as dots. Not everybody's favorite thing to do. Double bond this thing up on both sides because this looks more chemistry-like. And that, by the way, is how the dots get there, and they should be there. So you want to make sure you follow that order of single bonds first, place all the dots of electrons, and then you could go from there. So make sure you don't kind of jump the gun. It's a very common mistake. When we look at this, is everybody good? No, which one's not good? It is, right? It's only got 2, 4, and 6. Everybody else, again, here has 8 electrons. So at this point, we are going to try to fix it by making a double bond. And it does not matter which one you take it from because both oxygens are identical to each other. Remember that when we make the double bond, we're actually going to take a pair of electrons and bring them in to make that double bond. And that will get us a page that turns. But if we come back, it will give us a double bond over here. And we will still have our single bond on this side. This is one of those ones where we could also draw the double bond on the left, and we could draw a resonance structure for this. And if we did that and we double bonded the left-hand side, it would look something like this. And again, those are resonance structures of each other because we have more than one option. Obviously, in a question like this, where you're just asked to draw a Lewis structure, either one would be appropriate to draw. If you're, again, are asked to draw the resonance structures for everybody, you would have to do both of them. Any questions on that there? So that is what it should look like. And if you follow, again, those steps, that is the picture you should end up with. And again, very often people will just double bond both of those things, no dots on the central atom, because they just kind of skip to that and stuff like that. Any questions on that one? All right, we'll go here to NH4 plus next. We got 5 for the nitrogen. 4 times 1 for the hydrogen, and a +1 means that I have lost an electron, which means I actually need to subtract an electron from that for the plus charge. That's going to give me 9 minus 1, which is 8 valence electrons. This one's straightforward. We can only put nitrogen in the middle, as hydrogen should never end up there. We're just going to put hydrogens around and draw a single bond from the center to each of the outside atoms. In this case, that is 2, 4, 6, 8. Who do we appreciate? That is it. There it is. Yeah. So that's going to do it for the nitrogen there. Also, each of the hydrogens has 2 electrons, so a little bit of bracketing there and a positive charge on the outside. Question on that one there. All right, let's roll to nitrogen. So nitrogen is N2, so that is basically 2 times 5, which is 10 valence electrons. In the case of nitrogen, there really is not a central atom. There's just 2 atoms, basically. So you can do the same steps, you just put them side by side instead of obviously one in the middle, since there is not really one in the middle. So we're going to go side by side and do our same process, which means we're going to connect them with a single bond. That is 2 electrons at this point. We have 8 more to go. We're going to put them on the outside still as dots. So 2, 4, 6, and 8. Now we have placed all 10 electrons, and hopefully you can recognize the nitrogen on the left there is pretty short, right? It has only 4 electrons. The nitrogen on the right's all good, but the one on the left only, again, has 4 electrons. So at this point, we want to make a double bond to see if it fixes it. We are again going to take a pair of electrons in to do so. And when we do that, we will end up with something that looks like this. And did it fix it for the nitrogen on the left? It did not. It got better, right? It's at 6 now, so that's closer to the 8. There is no other option right at this point to make any other double bond, right? So our next approach should be we need to go to a triple bond at this point. Triple bond works the same way. We're going to bring electrons in to make the extra sort of bond. So we're going to take this pair of electrons and bring them in here to make that triple bond. And that will get us our triple bond now between the 2 nitrogens. And now is both nitrogens okay? They are. Both nitrogens now have 8 electrons and only a total of 10 total electrons between the 2. And that is how nitrogen gets to a triple bond, in case you were curious. That is basically how it does so. Any questions on that? So again, the order is, as you're drawing these, you kind of want to go single bond first. Somebody doesn't meet the octet rule, you want to move to a double bond, sort of exhaust all your double bonds, and then move on to a triple bond. So those are the orders that you want to follow. Again, should get you to a pretty good picture when it's all said and done. Any questions so far? All right, we'll continue on here with CO3 2 minus. So valence electrons 4 for the carbon. There are 3 times 6 for the oxygen. And in this case, we have a -2, which means we do need to add 2 electrons in there. So that's going to be 18, 20, 24 electrons. In this case, carbon and oxygen are in the same row on the periodic table. Oxygen is further to the right, which means carbon should be in the middle. And we only have 1 carbon to begin with, so that's a good place for it. So we're going to do a little deal like this. Just like before, we're going to do a single bond around. So 2, 4, 6, 8. We're going to put the rest of the electrons on. So 2, 4, 6, 8, 10, 12. 14, 16, and 18. 18 plus the 6 we started with our single bonds is 24 electrons. Is everybody good in this case? No, carbon is actually short. It has 2, 4, and 6 electrons only. The oxygens are okay. They all have 8. So in this case, all the oxygens, much like nitrate, pretty much are equivalent to each other. So we could take a pair of electrons and bring them in to do so. And we'll make our double bond there, and we'll do this. I'll look something like this. And again, a little bracket and a -2. This obviously, as you probably can imagine, is another one that we could draw several different structures for, these resonance structures. So we could have double bonded there to the left, and it will look something like this with a double bond over there. And obviously here we could also double bond it to the right, and it will look something like this. And once again, these are all what are known as resonance structures of each other. Any questions on that one there? The next one is CO2, I think is what we got up there. So we got 4 for the carbon, 2 times 6 here for the oxygen. That's going to be 12 and 4, 16 valence electrons. Much like above there, carbon is going to go in the center as it's the least electronegative. And we'll do a carbon, an oxygen, and an oxygen. We're going to do our single bond. That's going to be 2 and 4 electrons. At this point, we got 12 more to go on the outside first in pairs. So 2, 4, 6, 8, 10, 12 at this point. So at this point, I have now placed 16 electrons. And again, you could hopefully see that the carbon is not good. The carbon only has 4 electrons. So we're going to make a double bond and see how we do on this case. So we're going to bring a pair of electrons in to do so. And that will give us our double bonded oxygen. Did it fix it in this case? It did not. Again, we got better. We're up to 6 for the carbon. So this is a situation like I was just talking about that you could triple bond, but for reasons outside of this class, you probably shouldn't in this case. But you do have an option here to double bond on the other side. So because we do have that option, that's sort of what you would want to do in a case like this, is sort of exhaust all your double bond options before you kind of move on to a triple bond. So we would take the electrons here and bring it in for another double bond on the right-hand side, again, before we jump into triple bonding things. And now what we got going on there is a good picture. We got 16 total of electrons. The carbon now in the middle has 8, 2 and 2 on each double bond. And the oxygens also have 8. Any questions on that there? Last one I think I put up there was nitric acid, looks like. So let's take a look at this one. Nitric acid is a little bit different. So if it is something that you might not be familiar with, I would probably tell you how it's sort of connected. So this guy is kind of connected like I drew there, where actually the hydrogen is attached to an oxygen rather than to the nitrogen in the middle. And we will still do our same process, even though we actually have 2 central atoms here. We have hydrogen, which is 1. We got nitrogen, which is 5, and 3 times 6. So that's 18, 19, 24 valence electrons. So although there are more elements here involved, it still works the same way. We're just going to connect everybody up with a single bond. So everybody just gets connected with a single bond, just like normal. Now we have used 2, 4, 6, 8 electrons in this case. And we got then 16 more to go. We're going to work from the outside in, putting on our electrons. Do I put any on the hydrogen? I do not. So I'm going to put some over here on this oxygen, right? 2, 4, 6. Some on this oxygen, 8, 10, 12. That sort of fills up the outside. The next outside atom would be the other oxygen, right? That's to the right there. And we'll put some electrons in over here as well. And I think at this point I have 24 electrons on this picture. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons all the way around. Now, what we want to make sure is everybody's good. Is everybody good in this case? It is the nitrogen, right? That is short. So the nitrogen right here has only 2, 4, and 6 electrons. So just like before, we're going to make a double bond to try to fix that. In this case, frankly, I would choose either this oxygen or this oxygen. I might not choose this oxygen because that's pretty much what makes it an acid, is that hydrogen that pops right off in that polar bond. So I probably wouldn't double bond too much over there, but it is possible. So in this case, we're going to take a pair of electrons into double bond, and that will give us something that looks like this. And you could also draw a resonance structure for this guy as well, where perhaps we double bonded to the left instead of up on top. And it would look something like this. Any questions on that one? So you still follow really the same process, even if there's more than one central atom. In this particular molecule here of nitric acid, the nitrogen would be considered a central atom, and so would the oxygen in this case. You can come across obviously things that have multiple central atoms. A lot of organic molecules and stuff like that have multiple central atoms. But I would say a vast majority of what you draw in here will probably have one central atom and everything attached. And again, should always obey the octet rule in our drawings. Any questions on any of those drawings? How to draw Lewis structures for covalent compounds? Okay. That's what we did. All right, so we talked a little bit about resonance structures, but let's talk a little bit about bond length and bond strength. The bond length is the distance between basically two atoms within a bond. And you do not have to memorize these numbers or anything like this, but let's just talk about the general sort of trend that we see here. If we look at the carbon-carbon single bond, double bond, and triple bond, the single bond's 154 picometers, the double bond's 133, and the triple bond's 120. We look at the carbon-nitrogen single, double, and triple bond. What we actually see is every time we add a bond, make a double bond or a triple bond, the distance between the atoms gets closer because frankly, you're bringing more electrons between them, right? Which are negatively charged, going to bring those nucleuses closer together. So you got a single bond, which is longer, add a bond to make a double, everybody moves closer. Triple bond, everybody moves even closer because you're bringing a lot more negative charge between the two atoms, and that's going to pull everybody's nucleus right closer and closer together. So again, you don't need to know these numbers, but you do need to know what we see here, that a single bond is longer typically than a double bond, and a double bond is longer than a triple bond. It's not like twice as long or three times as long, but that's just a general trend. That also relates to bond strength. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. I think of it like a brand new pencil, right? Take a brand new pencil right out of the box. It's nice and long. You could take that thing and snap it pretty easy, right? You take a chemistry test or two, you're down to like a nubbin and an eraser. Good luck trying to break that, right? Very, very hard to try to break that pencil at that point. And that's what happens again as everybody kind of gets closer and closer together. They're going to be held tighter and tighter. It's going to take really more energy to break those things. If you had to break a double bond versus a single bond, it would take a lot more energy to break the double bond than the single bond. And it's all out there. So resonance structures, as we talked about as we were drawing, again, are structures. They're usually separated by these arrows. And really, it does sort of come about by having multiple places, as we talked about, where you could make that double bond. And you basically could draw an equivalent structure by just simply moving it around to a different location to make those double bonds at. And here are some of the examples, or some examples that we can see. This is ozone. You don't have to worry about the charges. Those are what we refer to as formal charges. But we could double bond ozone over here on the left. We could also move the double bond over there to the right. And again, the proper structure is probably somewhere in between those two, as those kind of double bond electrons are kind of moving from sort of atom to atom. And that's why we can sort of do these different types of structures. We saw our carbonate earlier. And again, case you're curious, that is where the negative charges are on the single bonded oxygens. That's why it's -2 is actually where it has. Benzene is an organic molecule that when you get to organic chemistry, you will draw nonstop. Looks something like this. It's actually has 3 double bonds. These are all carbons, actually. Everywhere there's kind of a point. You could also draw a resonance structure. Looks something like this. And sometimes you'll see, not in a true organic book, but it's non-fake organic book, I suppose. Sometimes people will just draw it with a circle in the middle to indicate that those electrons are sort of moving around from one location to the next. We won't see too much of benzene in here. All right. And here's obviously an example of several different resonance structures you could draw with something that has multiple double bonds going on. All right, let's talk a little bit about a couple of exceptions to the octet rule here to finish it out for today. There are some exceptions to the octet rule, but again, everything that we draw in here will follow pretty much the octet rule. The first exception to the octet rule is it was known as an incomplete octet. An incomplete octet is much like it sounds. There are certain things that are pretty much good with less than 8. Your most common one is going to be this guy right here, our boron. Boron is perfectly fine with 6, is sometimes known as being electron deficient. Aluminum and beryllium are also included in that, but most of the time boron is going to be probably your covalent bonded guy, and probably most of the time that you will see in terms of an incomplete octet is something with boron. But again, aluminum and also beryllium is sort of included in that ability to have less than 8 and still sort of be happy with that. A couple of other important exceptions to the octet rule is a odd number of electrons, and that is a situation where you do add up all your valence electrons, you end up with a odd number, which means if you have an odd number, you're going to have one unpaired electron. Like in atmospheric chemistry, free radicals, chlorine does that a lot. They're very, very reactive because they have one electron. Not so happy about that, want to kind of fix that. So they're very reactive to try to get that going on. So NO and NO2 here are examples of that. You can see it has one unpaired electron. And probably the granddaddy of them all, which is the expanded octet. That is probably the exception to the octet rule you will see the most, especially when you go to 1A. That will pretty much be everything you draw is like the expanded octet. And the expanded octet, much like the name implies, is something that can be happy with more than 8 electrons. And typically, if you look at the periodic table where sulfur is, and you go to the right, to the left, and down, they have the ability to go over 8. And that is because on sulfur is located, they actually have what are referred to as d orbitals available to them. And although they may not be using those d orbitals, they have somewhere to stash all the extra electrons. And d orbitals don't start until you get to right around sulfur. And that's why anything above it on the periodic table, like nitrogen, oxygen, and those guys, can never go over 8 because they don't have those orbitals available to them to stash the extra electrons. But sulfur, right, left, and down in the nonmetal region, they typically can go over. As you can see here, if we just drew the fluorines attached without all the other electrons for this particular guy, it has 2, 4, 6, 8, 10, and 12 electrons. So things could go up to 12 electrons, 10 electrons around the central atom, and it's perfectly fine. That's an expanded octet. You see it all over 1A when you get there. Just to